Hello everyone and welcome to this session about databases on AWS. My name is Russell Nash. I'm a solutions architect with AWS and I've been working with databases for many years, so I'm looking forward to spending some time with you and talking through some of the database options within the AWS cloud. So let's have a little chat about the database. Now the database is probably one of the most important pieces of technology that's underpinned our technology stacks for many, many years. It's been an absolute stalwart of transactional systems, analytical systems, payment systems, reservation systems, you name it, somewhere in the architecture there is a database. And what's happened over the years is that because of its ubiquity in almost everything that we do, we've actually asked the database to do a lot for us. So initially we used it for transactions and complex queries, but then we started to use it as a search engine. We would put data in there and try and search it. We then obviously wanted to analyze the data that was in there, so we started running analytics within there. We wanted it also to do hot reads for us, to do very low latency lookups. We also sometimes use it as a logging system, so we'd actually put logs in there and expect the database to hold it. And then we, as the web took off, we started to underpin websites with a more interactive type of flavor, and we needed a database for that to be able to serve up dynamic content and to potentially accept content from users. And as the web grew and more users came on, we then needed the database to provide kind of web scale throughput, as we call it, where you could have potentially many transactions a second that you need to deal with. So not surprisingly, the database started to creak under this kind of strain of being able to support all these different workloads. And so what then happened over time was that different engines, different dedicated engines started to appear to actually pick off some of these use cases. And if you look at what some of those are, and I've used the Amazon services here, but obviously there are many other examples out there in the industry. We've now moved to much more of a best of breed type of model where we really look at the workload and say, where's the best place for that workload? And so you see that we have Amazon RDS, which we'll talk about today, which is our relational database service, and that's the traditional database that you think of, and that's still used for transactional type of systems and complex queries. But a lot of people now are moving rich search off to dedicated search engines such as Elasticsearch. Analytics is often moved off to a dedicated analytics database, maybe something like Amazon Redshift. Hot reads is often best served from some kind of in-memory database, so we see a lot of caching technology used, so we have Amazon Elasticache for that. Logging, much better off putting logs into somewhere like S3, which is obviously very low cost and very scalable. And then for that web scale throughput where you need that persistent database but you need extreme scalability for reads and writes, that's where people have turned to NoSQL to really support that use case, and we've got Amazon DynamoDB is the Amazon service that supports that. So you can see we've kind of broken these out, and where we want to focus today is really on the four blue icons there. So RDS, Elasticache, Redshift and Dynamo. Talk through how they work, what customers do with them, and potentially where some of the trade-offs might be. So this is going to be our agenda. We're going to talk through these four, starting with RDS and then moving across to the right-hand side. Now, one of the things I wanted to point out here is that these four are what we refer to as managed services, managed databases within AWS. Now, those of you familiar with AWS would know that we have EC2, which is a basic building block within the AWS cloud, and that is a virtual instance of either Linux or Windows that you can spin up in various configurations depending on whether you want more CPU or more memory, etc. And then you can then treat that as you wish. So you install whatever software you like on that. So you could install a database, you could install a caching system, whatever you like. What we do with the managed services or the managed databases is we try and take you away from some of that heavy lifting that you need to do when you're actually managing those instances yourself. So let me kind of talk a little bit about that and show you what I mean by that. So if you're running a database in, say, a traditional data center, for example, then this entire stack your organization needs to manage. And down the bottom you see it's basically, that's really as low as it goes. You need to provide power and cooling to the servers themselves, then you need to rack and stack, etc., all the way through to maintaining that server, installing the operating system, patching the operating system, then installing the database, patching the database, and so on and so forth. And there's a lot of layers you've got to get through before you actually get to the top, which is really where the skill sets that a lot of customers are really looking to provide, which is the actual schema design and some of the internal database optimization, the indexing and the query construction. So if you do move to EC2 as your infrastructure, then you can see that some of that work is taken from you. So those bottom four there, so certainly in terms of the power and cooling and server maintenance and the installation of the operating system, that's something that we do. So that's what EC2 provides you. That's going to be a virtual instance, and so we do all that for you. But from then on, including from kind of patching the operating system upwards, that's still something that you would need to manage. Now, if you then take it one step further and you look at a fully managed database, which is what we're going to talk about today, you can see how much more of that stack is taken off your plate and onto our plate. So all the way up through to patching the OS, installing the database, patching the database, backing up the database, and then things like high availability and scaling and things like that. So a lot of the things that keep a lot of DBAs up at night. I know a lot of friends who don't sleep particularly well, and a lot of it's around high availability and scaling. So by using a managed database, a lot of that worry is taken off. And as I was saying before, those top three, this is really the value that you want to bring. This is the skill sets that you really want to bring to the table is whatever's happening in the database, creating the right schema, making sure the indexes are in place, making sure that the queries that you're running are as fast as they could possibly be, and let us take care of the rest. So let's have a little look at RDS first. So RDS stands for Relational Database Service, and as I said before, it's really often referred to as these breed of databases are traditional databases, if you like. There's a choice of engines, and a lot of them would be familiar to you. So there's a couple of commercial engines there, Microsoft SQL Server, Oracle, and then you can see the open source ones there, MySQL, Postgres, MariaDB, and then Amazon Aurora as well. So Aurora is an Amazon developed database that's 100% compatible with MySQL, so very easy to migrate to Aurora if you're already using MySQL. And as I said before, one of the attractions of RDS over running databases yourself is that low administration, that we take a lot of that heavy lifting off you. So let's look at that in a little bit more detail. Let's look at some of the things that RDS provides that can make your life a little bit easier. So firstly, obviously, backup and restore. So one of the things that RDS provides are automated backups. So we'll take a full database backup for you once a day, and then we'll also back up the transaction logs as well, so that if you need to, you can go back to a point in time up to whenever the last restore point is. Now, we'll manage that process. We will archive the backups across to S3. So S3 obviously gives you extremely high levels of durability, and we will manage that process for you. In addition to that, you can also take your own database snapshots. So some customers are happy with the automated process. They also want to manage their own database snapshots at a particular point in time, so they always know they've got a snapshot that they can then restore and then have that up and running. Another thing that people who manage databases are interested in is monitoring and alerting. So you can get some very detailed metrics from the database in terms of how it's performing, so that you can make sure that the database is performing as it should. There's over 50 metrics that you can pull off and have a look at. And then obviously you can set alarms and notifications on that as well. So if CPU utilization goes over a certain threshold, then you can be alerted about that. That's all built into the RDS service. Now, probably the biggest pain point that I hear when I talk to customers about managing a database is high availability. It always comes up that the database has become so important to our organization that we cannot have a situation where we lose the database for an extended period of time. So within RDS, you have the option to choose a multi-AZ instance. So the way this works is that within an Amazon region, so let's say Sydney is a region, and within that region we've got multiple availability zones. Now an availability zone you can think of as a separate physical data center. And so what you can do is you can deploy your primary instance into one of the AZs, AZ1, and then point your application at that. Now you can leave it at that if you wish, but if you want to have that high availability option, you can simply tick the box. So if you're doing this through the console, you can just choose the drop down. If you're doing it through the SDK or through the CLI, there are commands to do this as well. And you basically say, when you deploy this instance, I want it to be a multi-AZ type of deployment. What that means is that we will then spin up a secondary instance in a different availability zone, and we will then manage the synchronous replication between the primary and the secondary. It is synchronous, so that means that those two databases are always in sync. So what happens is, of course, all your writes still need to go to one place, go to the primary, and you can't use the secondary for any kind of read traffic. We'll talk about how you manage that a bit later on, but that secondary is simply there just to sit there in case you need it. So let's say there is an issue with the primary. Let's say it's unreachable for some reason. What will happen is the secondary instance will be promoted to be the primary, and at the same time we will then update the DNS so that your applications will now point to the new primary. They can then issue their writes there, and then we will then bring up the secondary as soon as possible. Now that multi-AZ approach has other knock-on effects as well. So for example, if you need to upgrade an instance, for example, we can then upgrade them separately. We can upgrade the secondary first, things like that. So it really gives you a little bit more flexibility in managing your deployment. In terms of performance, there's a couple of options that you have here. So one of them is the instance class that you choose for your database. So underlying RDS are EC2 instances, and you tell us which of those instances you want to run with your database. And as I said, they've got different capabilities in terms of the numbers of CPUs and memory and network, etc. So you choose the instance class that you want, and then you also choose the storage type that you want to go along with that database as well. So let's delve a little bit into storage types. So there are three storage types that you can choose. There's the magnetic storage type, which is a hard drive. I had a customer the other day refer to these as spinners. It took me a long time to work out what he was talking about, and then I realized that he was referring to the good old spinning magnetic disks within there. And then we have the general purpose, which is SSD backed, and then we have provisioned IOPS, which is also SSD backed. So how do you choose between these? Well, basically, if you look at the general purpose in the middle, that's where most applications will sit quite happily. That's for really for kind of most of the workloads that we see. On the left, you might go with magnetic for maybe small database applications that work fairly infrequently accessed. So you can, it's obviously it's online and queryable, but it's not as fast as the SSD ones. But you can use the magnetic disks there to keep the cost costs down. And then on the right-hand side, the provisioned IOPS is where you actually tell us how many IOs per second you want. So that's what an IOP is. It's an IO per second. And you tell us, okay, I want this level of provisioned IOPS. So this is where you'd go if you had an extremely highly transactional type of application where you really need that number of IOs per second to support that. Now, I talked before about having a multi-AZ setup gives you that high availability from the standpoint if there's something wrong with the primary. And I also mentioned that you can't use the secondary for read traffic. So what happens if you do want to spread your read load wider than just the primary instance? Well, what you do there is you use something called a read replica. Now, what the read replica is it's completely separate to the multi-AZ situation. So you can see we've got the multi-AZ set up there. So we've got the primary, the secondary, they're in sync. The read replicas are set up, again, they're separate instances, but they are asynchronously replicated to from the primary. So we'll actually propagate any changes from the primary across to the read replicas, but there may be a slight lag there because it is an asynchronous, it's an asynchronous replication. So what that means is that if you think about your application, if you need to do any consistent reads, then that still needs to go through the primary. So a consistent read means that if you write something and then you read it, it should be there. Or if you've done an update, that your read should reflect the update. That's a consistent read. So if your application needs a consistent read, you do that on the primary. But often we find that there's a lot of applications where you can actually use eventually consistent reads, where it's actually not crucial that you get the most up-to-date information. The application can tolerate some lag there. So if that's the case, you can actually then start to use read replicas to take some of that read load off your primary. And obviously you can bring read replicas up for a period of time if you had a particularly, if you knew you were going to have a heavy day in terms of read traffic, and then obviously you can then shut them down once you don't need them anymore. Again, very easy to set up within RDS, and again, just something that takes some of the pressure off you guys to set that up. An interesting customer that uses RDS is Literacy Planet. So this is an online resource that is designed to help kids with their literacy skills. And the interesting thing about Literacy Planet, they actually use RDS, but they also use DynamoDB, which we're going to talk about later, and they use Elasticache, which we're also going to talk about later. And you'll see this is a bit of a theme as we go through, that even though we've talked about this session as being how do you choose between a relational or a NoSQL or a caching scenario, a lot of customers will use them all in conjunction with each other. Often it's not about choosing one over the other, it's about using them together. So Literacy Planet, one of the things that was important to them was that the infrastructure didn't overburden them in terms of administration. And so Richard Glue, their CTO, he talked about that if he had set his environment up in a physical data center, he would have needed at least 3 administrators to maintain the infrastructure and the similar levels of availability. So I think that talks to some of the attributes we're talking about with RDS, where it just takes a lot of that heavy lifting away from you. So let's move on to Amazon Redshift. Now, Redshift is an MPP database, which stands for Massively Parallel Processing, but it is a SQL database, and this is important that you still drive it using SQL, ANSI Standard SQL, but it is optimized for analytics. So whereas RDS is more of a mixed workload, it will do transactional workloads, and obviously to some degree it'll do analytics as well. Redshift just does analytics. It's just designed for the analytical type of workload. Now, because it's MPP, because it scales horizontally, you can actually drive it to very large volumes if you need to. So you can start quite small in the gigabytes, and you can get that up to the petabyte range if you need to. And it's also fully relational. So even though there's some different architectural things underneath the hood to give you that performance, it is a fully relational database. You still create tables, you still join them in the same manner. So if you're a current user of a traditional database and you're thinking about going to something like Redshift, the actual leap in terms of the concepts that you need to learn is pretty small. There's not a lot to get your head around. You just need to kind of bend your brain around some of the parallel aspects of it. But in terms of data models and schemas, it's very similar. So looking a little bit under the hood at Redshift, you can see the leader node there is the node that all of the SQL clients connect to, and it's the compute node underneath, that compute node layer, that you scale out as you need to. So the idea with a massively parallel database is that you spread every single table across the cluster. So if we look at this very simple table here, within the cluster it's going to look like this. So every node is going to have a small slice of that table. And so the idea is that then each node does its own work independently of the others. So the SQL query comes in, the same query gets pushed to every node, it's working on just its slice of the data, gets an intermediate result set back, and then passes that back to the leader node. So you can see that's why you're able to scale it to very large volumes, is because you're adding these independent nodes that aren't going to clash in terms of getting resource. Now there's a couple of other things that Redshift does under the hood that add to its ability to allow you to do these analytics on very large volumes. And they're all to do with reducing the amount of I/O that a query does, reducing the number of times that Redshift has to read from a disk. And the first thing is that it's a columnar database. Now, all this means is that Redshift will store the data in columns rather than in rows. So if you think about the way that a traditional row-based database stores the data on disk, it's exactly as your brain imagines that it does. So if you think about that small table that we have there, a row-based system would actually store the rows all together. So it would store the ID, the age, the state, the amount, then the ID, the age, the state, the amount. Now that's great if you're doing transactions, because you want to be able to write a whole row at a time, or read a whole row at a time, or delete a whole row at a time. However, in an analytical system, typically you're not looking at every single column in your query, but you probably are looking at a very large number of rows. So in a row-based system, it's actually very inefficient because you're having to read a lot of redundant data. So let's say our query is give me the average amount by state. I've still got to read the ID and the age, even though I actually don't need it in the query. So if you look at the way that columnar databases store the data, because that data is going to be stored, all the IDs are stored together on the disk, all of the ages and then the states and then the amounts. If I need to run a query like give me the average amount by state, then I can simply go to the blocks on the disk that contain the data I'm after. Now, the great thing about a columnar storage is it's something that Redshift does underneath the covers. It's not something that you need to worry about either in your design or in your queries either. It's something to be aware of when you're designing, but it's not something that you need to necessarily change. The other thing we do underneath the hood is we compress data as well. Now, as you all know, you've always been told that there's a trade-off between compression and performance, and it's either one or the other. In this particular instance, we actually compress for the performance, which sounds a little bit counterintuitive, but what's happening is that, again, we're trying to reduce the I/O. So we've got blocks of data on the disk, so we've got 1 meg blocks of data. The more compression we can get on your data, then the more data we can get into that 1 meg block. So if we're getting, let's say we're getting conservatively, we're getting 2x compression, we're getting 2 meg of your data into that 1 meg block. Now, because we can decompress extremely quickly when we pull it off the disk, that means we're actually essentially scanning much more data with each disk read. So compression in this case is a good thing and leads to actually faster performance. The other thing we do within Redshift is make use of zone maps. So what zone maps do is they try and minimize the number of blocks that we're going to hit on the disk for a particular query. Now the way that works is that if you think about a block of data on the disk, so let's just say this is a 1 meg block and there's thousands and thousands of dates in this block, because remember it's a column and database, so all the values in this block are going to be from one column. Now when we run a query, we want Redshift to know whether to read that block or not. So what the zone map does is it keeps a minimum and a maximum value for each block so that we can actually work out what range is actually in the block. So if we ask a query like this, we're actually asking for a very specific date, or it might be a date range. Redshift will query the zone map first, so the zone map's in memory, so it's a nice fast lookup, and it will say, is there actually any data within this block that's of interest to this query? Because if there's not, then I'd like to skip it. And so we can then work out which blocks to read and which blocks not to read. Now you can imagine as you start to grow your database and you've got more and more data in there and more history, this becomes very, very important, because you may only be asking for yesterday's data or last week's data, but you might have 5 years of history in that table. So the zone map is a way that Redshift can basically ignore all of the data on disk that's not going to satisfy your query. Socrati are one of our Indian customers, and they're one of the biggest advertising technology companies, and they do a huge amount of analytics on vast amounts of data, and they use Redshift for that. And the interesting thing I think here is that they have quite a lot of data today, but they actually project that they could grow 100x in the next few years. Just think about that for a sec. 100x, that is an incredible amount of growth in terms of data. And so the nice thing for them, they're using Redshift now, so they know that they can simply scale with the system that they have as they need to. They don't need to provision that amount of data up front. They can grow as their data volumes grow. So that's Redshift and analytics. Let's have a little look now at DynamoDB. Now, NoSQL is fascinating, I think, because it was not only is it kind of wear its heart on its sleeve in terms of the name. So basically, you know, we are NoSQL. We're taking a stand against SQL. So it stands for NoSQL or not only SQL, depending on who you talk to. But either way, it was really a stand against the traditional relational database to say that as soon as we're trying to serve dynamic content on a website, or we're trying to accept input from a user, as soon as those volumes go up, the traditional databases can't handle it. And as with everything in the technology world, there was a trade-off to be had there. And the trade-off was between the scalability but also data complexity. And when the NoSQL guys kind of looked at the traditional relational databases, they said, actually, we don't need the complexity, we don't need all the bells and whistles that come with relational databases. So if you look at a relational database, you look at the lovely rich data structures that you have in there, that's fantastic, but what you trade off is you can't scale them to massive volumes. You can push them pretty hard, but they do tap out at a certain level. So NoSQL was born, and NoSQL said, we'll fix that, we'll trade off that complexity, and we'll give you scalability. Now there's actually some nuance in there as well. There's a few different kind of subgenres of NoSQL database. The most basic is the key value, where you have a primary key and then a value that gives you the best scalability. But then you can also introduce some more complexity with document databases as well that often have JSON values in there as well, potentially nested. And then graph databases, which are great at looking at relationships between entities. So that was really where NoSQL was born. Now, to just have a look at that a bit more closely, what do we mean when we talk about you know, a relational table versus a non-relational table? Well, if you look at a relational table, there's a very simple one there, looks like that. And that table may have relationships with other tables. So it might be that we have another table where those IDs actually mean something. Maybe they're somebody's name or their address or whatever it might be. If you look at a non-relational table in a key value store, it's much simpler. So you still have the same ID, but then you have these attributes, and the attributes are much more flexible than you have in a relational system. So in a relational database up the top, when you load data in there, you need to load the age into that column. You need to load the state into the state column. If you have an extra bit of data that's not in your table definition, then you can't load it in. You have to change the table definition before you can load it in. And that was another thing that a lot of the NoSQL proponents said from the beginning. They said, this is just too inflexible. Sometimes we just don't know what data we're going to want to put in there. We need a more flexible approach. So down the bottom there, you see the key value approach where, yes, you have the key, but then you just stick in the attributes and you name them. So if you have the age and the state, that's fantastic, you put it in. But if you end up with country and gender and whether they're a smoker or not, you just shove that in there as well. If there are attributes you don't have, that's fine, you just don't put them in. And so that it gives you an enormous flexibility, especially when you're ingesting data, so that you don't have to kind of conform to that schema. So DynamoDB is a NoSQL database. It started off as key value, but we've added document capabilities to that as well, so you can have JSON documents in there too, and it gives you that very low latency that you require for kind of web scale applications. And it's also fully managed. So we've talked about this a bit, but managing NoSQL databases can be a little bit tricky, and so we try and take that pain away from you by making sure that we give you that fully managed approach. What do we mean by low latency? Well, we mean that even as the number of requests goes up and down, the average latency should remain nice and consistent, because that's what you want. You want that consistency for your consumers, whether they're writing data to you or whether they're trying to read data. You need to know that it's going to be delivered very quickly. And then in terms of that being fully managed, what kind of things do you get with that? Well, durability is obviously absolutely key. So DynamoDB sits across 3 availability zones. So we talked about availability zones being separate physical locations, and we will continuously replicate between those 3 AZs. And we use custom SSDs to do that, to make sure that it's nice and quick. Now, often one of the things that comes up with NoSQL is, well, what about this consistency with reads that we were talking about before? Well, with Dynamo you can actually choose either. So you can either have a strongly consistent read, which means if you write it and read it, you want it to be there, or you can choose an eventually consistent read as well. So we really find that customers have different needs depending on their application, so we leave it up to the customer to decide on an application basis what they want to do there. The other really nice feature of Dynamo is that in terms of it being fully managed, we actually take the fully managed bit to a whole new level. And so instead of telling us how many servers you want underneath the covers or how many nodes or anything like that, you simply tell us the kind of throughput that you want for reads and writes. So you tell us how many reads per second you want, how many writes per second you want, and then we will take care of the infrastructure underneath to support that. So it's very, very easy to dial it up and dial it down, and it just takes, again, all of that management off your plate and onto our plate. For those of you wondering, that dial goes up to 14, which is 3 more than 11. Very interesting customer, V-Air. So these are one of our Asia-Pacific customers. So these guys are a low-cost airline. Now, obviously, if you're using a booking engine, that needs to be fast, and it also needs to be extremely available and durable. So they use Dynamo for that because they need that performance and also the durability as well. Interestingly, they also, similar to Literacy Planet, they also use MySQL and they also use Elasticache. So again, you can kind of see that often customers will use a variety of databases to do what they need to do. And I think that the quote here was really interesting that, I mean, these are business critical systems for a lot of customers, you know, where if their booking engine goes down, that's obviously business that they're losing. So, so that was a nice quote there to talk about the resiliency of some of these systems. So that's web scale throughput. Now what about hot reads? So we've talked about Dynamo being extremely fast, and we've talked about it being, and when we talk about fast, we talk about typically single-digit milliseconds, which is pretty fast. But would you believe, for a lot of applications, that's simply not fast enough. Customers want even quicker performance than that. So that's where hot reads come in. Now, where do you get hot reads faster than that? You get that from a memory-based system. So Elasticache is, again, it's a managed service, and it's an in-memory key value store. Very, very high performance, and it runs a couple of open source engines. So it runs either Memcached or Redis. Redis being extremely popular because of its very rich language support. And what do we see in terms of is that it's a caching layer for, obviously, for performance. So you put that cache in so that you get extreme performance. But also sometimes customers will use it as a cost optimization technique. So if you've got a database sitting in the back end that is getting hit a lot with a lot of read traffic, then you're going to need to scale that database, obviously, to meet that traffic. Now that can get very expensive, and what a lot of customers find, if they put that caching layer in front of it, you're actually protecting the database from a lot of that traffic, which means you can actually scale down and use a smaller instance. So often the cost benefits of having that caching layer can be quite marked. Another use case we see is storage of ephemeral key value data. So the key word here is ephemeral. So it is an in-memory system, so it's not as persistent as, say, any kind of database where you're writing to disk. So you need to obviously pick the right use case here that, yes, you're getting extreme performance, but make sure that you don't necessarily need that persistence. And then we see people using it for things like leaderboards, for example, especially in gaming. And there's some nice features within Redis now where you can actually have sorted lists within there, so the database will actually do the sorting automatically for you. So especially with things like leaderboards, you know, you're whacking the changes in there, and then when you do a read, you want top 10, you want to know exactly what the leaderboard looks like. Also, session management is a key one, obviously, as well. So managing the session state for an application, event counters, and in-memory lists as well, we see used for that. So what does a caching architecture potentially look like? So this is one of the use cases we talked about where here we have an application sitting on EC2. It's reading and writing from RDS. Now, if this gets hot, then this is where we might want to put in some kind of caching layer. So what we might do is we might put in Elasticache there, and what will then typically happen is you'll change your application to say, if I'm doing a data lookup, look it up in the cache first. If the data is there, then serve from the cache, which is nice, so that saves a trip to the MySQL database. If it's not there, then I do have to go to the MySQL database, route, serve it to the client, but also put it in the cache at the same time. And so over time, obviously, you then build up. Obviously, you're getting more hits in the cache than misses. So that's one of the basic architectures we see with caching. Grab Taxi, many of you up in Asia Pacific would be familiar with. so you can book taxis and private cars through them. And their comment here about their use of Elasticache was that the latency of the cab call must be low, and it remain low even in terms of peak traffic. And this is key. You need to be able to scale, and you need to be able to give your users that consistent response. So that's the basic walkthrough of the 4 different managed databases that we have. So I hope that gave you a nice overview of what they do, the value of the managed service, and also the delineation between some of those, but also gave you an understanding of the fact that a lot of customers will actually use a combination of these depending on their needs. And so it's no longer that kind of monolithic database serving every single need within the organisation, but it's about choosing the right database for the right task.